In section 3.2, we're going to look at measures of variation for a data set. In other words, we're going to look at quantitative measures of how spread out the data is. You know, is it tightly coupled around the center, or is it more spread out? So you see here that we've got the 5 starting players of 2 different basketball teams. So just by looking at the heights of all those individuals for each of the 2 teams, which one would you guess has more variation in the heights? Well, just by visual inspection, it seems like Team 2. If we look at the shortest and tallest starting players on the team, then we can see that it seems that Team 2 has more variation. So that's an example, a visual example of the range of a data set. And so to do the range of a data set, you just very simply take the maximum value minus the minimum value. A very, very commonly used quantitative measure of the variation present in the data set is the sample standard deviation, which you see there. Notice that little s squared would be the expression that you see above, except without the square root. And so typically we calculate the sample variance first. Can't spell today. Sample variance, which is the square of the deviation. But like I said, typically we calculate the variance first and then take the square root to get the sample standard deviation. And so if a data set has more variation, then the standard deviation will be bigger. So that's why the standard deviation is a good measure for the variation. First, we saw the defining formula, and here we have the computing formula. This is a formula that's a little more friendly whenever you actually have to do this computation. And again, to get the sample variance, you just remove the square root. So a little s squared will be the value of the expression above without the square root. So here let's look at, we have 2 data sets. Let's focus on data set 1. In data set 1, we see that the mean is 50 and the sample standard deviation is 7.4. So that means that the sample variance will be 7.4 squared. Now there's probably some rounding here, and 7.4 squared gives 54.76. Let's see how to do that. Here we will see how Microsoft Excel can be used to calculate the sample variance and sample standard deviation for dataset 1. So notice in column A we have the index I, which goes from 1 to 10. And then in column B we have the data, the xi's. And then in column C we take each data value and square it. And then column D, we take each data value and subtract x bar. Now remember the sample mean, to get that, we take the sum of the data, which would be the sum of column B, and notice we have that as 500, and then divide that by the number of data values, which here is 10, and so clearly 500 divided by 10 is 50, and that gives us our x bar. And then continuing column E, we have the difference of the data value xi and x bar, and then that difference squared. And the sum of that column E, is one of the primary numbers that we will need in order to use the definition of the sample variance to calculate. And you can see that is given here. So the formula is basically that sum of the differences squared divided by n minus 1, which in this case would be 9. And so 494 divided by 9 gives us 54.8, and then the 8 repeats. So that's the sample variance. That's using the defining formula to calculate. But now also, if you look on your formula sheet or look in the textbook, there is a computational formula which seems to be a little, let me move this down here, and then, well, I was going to put that one on top, but I guess that's not possible. Okay, so let's focus on the computational formula. With this one, we need the sum of the data, that's the 500, and then the sum of the squares of the data, which is column C, is 25,494. And then if you have those two numbers in addition to little n, which is 10, then you can use the sample variance formula as you see there. And that's a little bit more computational friendly, which is why that's the formula given on the formula sheet. And so now that we've calculated the sample variance, we just need to take the square root, and that will give us the sample standard deviation. Hopefully that gave us a good understanding of how to calculate the sample standard deviation and why it gives us a good quantitative measure of how spread out the data is. So now looking at figures 3.5 and 3.6, visually we can tell that it's the second data set that's more spread out. So if we look at the sample standard deviation, it should be bigger. And notice that what we're given here is x bar and then x bar plus s. So just from what we see on this diagram, the sample standard deviation for this second data set should be 64.2 minus 50, which is 14.2. And then if we do similarly with this data set up here, it would be 57.4 minus 50, which is 7.4. And so that makes perfect sense in regard to what we're seeing visually, because the sample variance here is 14.2, whereas the sample variance for the data set at the top is smaller, is 7.4. And visually we can see that the top data set is not as spread out as the bottom data set. There's a rule of thumb, it's called the 3 standard deviations rule. And basically what it says is that almost all of the observations will lie within 3 standard deviations of either side of the mean. So if we go back to our two diagrams, you can see that that's true in both of those data sets, because we're going from 3 standard deviations below to 3 standard deviations above. And in both cases, all of the data are between those two points.